This video is about discretizing. The various operators that perform discretization are used when numerical attributes can't be handled by whatever data mining operator follows. So the discretizing operators themselves change numerical attributes into nominals. The value of each nominal is based on the original numerical value after it's been placed into a particular numerical range, otherwise known as a bin. There are various ways to choose how big each bin is and where its boundaries are, and it can actually be very important to get these right. So we'll cover discretize by binning, the operator and its parameters. We'll cover discretize by size, discretize by frequency, by entropy, and lastly by user specification. It's important to realize that the discretized models also output a pre-processing model that you can use. It's very important to know how to do that. So we'll start with a process. As usual, it makes some data. As usual, again, the details don't matter. It outputs this subprocess outputs two example sets. One example set is multiplied up and then is applied to each of these discretize operators. This one is by binning, by size, by frequency, by entropy, and this is by user specification. Each discretize operator also outputs a pre-processing model, so in this one I'm applying that model to the other output from the sub-process here, which we'll cover that at the end. First things first, let's look at the data. So there are two outputs from the sub-process, both 7,500 examples, as you can see here. If I go to the statistics view, there's one attribute which I'm going to call original attribute, which is a copy of an attribute called attribute to discretize. You'll see that both these attributes are in the range 0 to 1. In addition, there's a label which has three values, 1, 2 or 3, and there's approximately 2,500 examples for each value of the label. If we plot a histogram of the attribute to discretize, you can see this is, as you saw, it goes between 0 and 1, and I have 100 bins set up here, so essentially I'm counting how many of the attributes are in the range 0 to 0.01, between 0.01 and 0.02, and you can see there's some structure in the data. There's a lot of examples, for example. There are a lot of examples at this particular range here, over 1,000, between 0.17 and 0.18 perhaps. So anyway, what the discretize operators are going to do are to split these numerical attributes, this single numerical attribute rather, into a set of nominal values based on a boundary drawn on this line here. Essentially what will happen is, if I scroll this over to here, if we for example pick 3 bins, it will try and partition the data into 3 bins. One of the operators does this, for example, but there are obviously other ways of doing this. But let's start though with, if we run the process to the end, let's look at the discretize by binning operator first. So we have the data here, but let's look at the parameters. So the parameters are like so. So first of all, as usual, you can choose the attributes that you want to apply the operator to. I've just chosen single and the attribute to discretize. I'm not inverting the section. There's no special attribute. The first important parameter is the one here, number of bins 3. So what's going to happen here in this operator is that the 3 bins will be defined, and the bin boundaries will be based on an equal division of the range of the attribute. So in our case, if I go back to the data, we know that the original attribute is just a copy of the discretized one here. The range is 0 to 1, so we're expecting to see ranges between 0, 0.3, 0.3 and 0.667. So you can see here, this is what has happened. You can see that the nominal value that's been created is based on a range of values that the attribute could take. So you can see the first range is from -infinity to 1/3. The next one is from 1/3 to 2/3, and the last range is from 2/3 to positive infinity. So this is dictated where the boundaries of the bins are, and this therefore allows each attribute to be placed in one of those bins. So if we look at the data, we can see that, sure enough, each attribute, this is just the original attribute, has been placed in a bin of some description. If I sort this column here, you can see that obviously value 0 has been placed in range 1, that's correct. If we scroll down slowly, we'll eventually see it change to range 2. About a third of the way down. Oops, here we go. So you can see it's coming, and sure enough, here we go. When the attribute was 0.334, that moves it over into the next range. There might be some subtle rounding errors there. I think there's probably not enough precision in my display. And we could go on, get to 0.666, and we should, there we go, 0.6 there. So the value of the attribute has placed it in range 2 because it's less than 0.667 in this case, but obviously in range 3 in this case. Okay, let's just take a look at what that looks like. So this is a histogram, a colour histogram in this case, and I'm plotting the original attribute against the nominal value or bin that it's been placed into. So you can see I'm choosing one bin, so what this chart view does, it puts one bin per colour. So it's showing that between 0 and 0.333 there are 5,200 examples that meet that criteria are in that bin. There are something like 1,750 in range 2 and about 500 perhaps in range 3. Quite interesting. If we move this ladder all the way up to the top here, you can see that the structure of the original data, if you remember the original data before we applied the processing, it was quite a complex sort of distribution. There's a bulge here, a tight peak here, and a broader peak here. So the discretization hasn't taken any account of this structure. Now that might be important. Other operators will do a different job, but it's important to bear in mind that this binning approach is very simplistic. Okay, let's just cover off the define boundaries parameter here. If I set that, what this will do is restrict the range which it will use to create the bins. It'll essentially mean anything below 0.1 is a bin in its own right, anything above 0.5 is a bin, and then between 0.1 and 0.5 3 bins will be created. Might as well run that quickly to show that happening. And here we are. So this was, if you remember, there are now 5 bins. You can see the blue one here is negative infinity to 0.1, which was the range we just said. This is 0.5 to infinity, which is here. So now it's done. It's now created 3 bins between 0.1 and 0.5. That's what's happening here. Okay. I'm going to turn that off though. Let's just cover off this last parameter here. Short and interval with different range name types. Might as well just show you what they mean. Long is what we've been using up to now. Short. This basically makes the name of the nominal a bit smaller. and you can see it no longer has any information in it about what the range of the attribute actually is. So this is range 1, range 2 and range 3. You can see them here. Range 1, range 2 and range 3. And that's fine, but I personally don't like to do that. I like to know where the attributes are, what their ranges are. So let's just change this last parameter here to be interval. I'll set this to be 3 digits. You'll see what happens in a moment. This has the effect of shortening the name. It's no longer range n, but it still has the range of the attribute in. If you change this, let's say put it to 2 decimal places, that has the effect of changing the nominal values to a smaller number of decimal places in this case. It's quite neat. But nonetheless, I still try to use long, which I use throughout this. So the next one is discretize by size. So again, I'm choosing the attribute to discretize to be processed. This operator takes a size of bins parameter. So what this means is it uses that number to make bins of approximately equal size, and this dictates the boundaries of the bins. Might as well run it. So if we look at the statistics, it's made 3 bins, and you can notice where the boundaries of these are: minus infinity to 0.158, 0.158 to 0.192, and then 0.192 to positive infinity. And you can see there's approximately 2,500 in each. So it's trying its very level best to get that number in each, and that's driven the boundaries. Now it's not exact because there will be attributes with the same value, so it can't put 3 examples at 0.158 in range 1 and 3 in range 2, so it has to pick one or the other range. Therefore there'll be a certain amount of jitter, I suppose, around these values. But let's have a look at what that looks like. So this is just simply a bar view. So each of the heights here represents about 2,500, and you can see they're coloured in based on the range. Better to look though at the histogram view. This gives us a slightly better view as to what's really happening. So I'm plotting here the original attribute, and I'm colouring it in based on the result of the discretized operation itself. So the ranges, you can see them up here: minus infinity to 0.158, that's here, and there are 2,500 in there. Between 158 and 192 here, there are again 2,500, and then there's a large range all the way up to positive infinity, essentially. And again, the number in this though is still 2,500. And if you remember, if we do this, you can get a sense of this is what the original data approximately looked like. And you can see that the boundaries are, well, maybe it's matching a little better some sort of structure that's going on in the data. Anyway, let's just quickly consider these 2 parameters here on the discretize by size operator. This first one dictates, I think, the order in which the nominal values are produced, decreasing or increasing. I tend to leave it alone, and long, short interval, as we saw in the previous operator. Let's move on to discretizing by frequency. This is similar to the previous one, discretized by size, except in this case we know how many bins we want, and we want them to be of equal size. So we can say we want 3 bins. So if we run that, we are expecting an approximately equal number in each. So again, if we look at the results, so again there are 3 nominal values, 3 bins, and if you remember from the previous one, the ranges are very similar. It was 0.192 in the previous one, it's 0.194. So there'll be some subtle difference to do with a particular value being repeated across a number of examples, which is driving this. But you can see essentially they're all the same. It's about the same number of examples in each of these bins. Again, if we look at the histogram view, it's similar to the discretized by size, similar boundaries. Let's go back to the process. So this is discretized by entropy. Now this is a more complicated one, although there are fewer, ironically fewer parameters. What this does, it requires, first thing it requires is a label. What it will do is try to partition the attributes into bins so that the entropy is minimized by virtue of the population of the bins with respect to the label. And there's a remove useless parameter here. It might be that you'll have an attribute which has values only for one label, in which case it's useless, so you could remove it. So I just leave that as the default. If we run that, we will see, again, what's happened is it's basically this time it's chosen more bins. That's just the way the entropy measure is working. If we look at the details, so it's basically chosen 5 ranges, and you can see the different numbers of examples in each one. And if we look at the histogram view, that shows you the relative numbers regardless of the absolute widths of these ranges. Let's look at the histogram view. That's more interesting. You can see that it's tried to put 2,500 in the first range and the last range, but it's, for some reason to do with entropy, it's decided that the best way to split this is to have 3 different bins. I think it's probably because there's an overlap of the labels around here, so it's doing its level best. But anyway, it's quite interesting that it's like a decision tree split that's going on here. So it's essentially split this in the way it thinks is best, and it's quite interesting that it's found the boundaries really without being told. So if you remember, here was the original data, and you can see that, you know, yeah, it's sort of found a place where the data looks interesting, and it might be valid to give that a different bin designation compared to the others. Okay, now the last discretized one is called discretized by user specification. Quite fiddly, this one. This is where you want to take total control. What you have to do is define the boundaries of your bins. So here's just an example, and it's important to get these in order. Basically, it starts at the top and reads down, so it'll look at each example and it will say, well, best if you read it from these class names. It looks at that one. If it's less than infinity, it moves on. If it's greater than that, well, it must be in this one. And it keeps repeating that. Best way to do it. Look at this picture, I'll run it, and then you can understand what goes on. Discretizing with user specification, here it is. So if I sort this, you can see that, okay, less than greater than minus infinity and less than 0.16. Well, that's true. So if we scroll down, eventually we should find that we get a change. Here we go. Okay, there we go. So that's the first boundary. Notice the less than or equal. So this name is the name I've given it because I know how it works. So it's less than or equal to 0.16. That's what's happened here. This is 0.16 greater than 0.160, so therefore it goes into range 2. And the reason I put 1 and 2 in front of the range is it means you can sort it more easily. So back in this view here, you can do this more easily, for example. Okay. Final thing, let's look at the apply model operator. So each of these discretized operators outputs a model. It's called a pre-processing model. It's just a model. and you can use the apply model operator to apply that to data. So if you remember, I made two data outputs from this make data subprocess. So this bottom example set here hasn't been discretized, so if I set a breakpoint before, we'll run it. So what you're seeing here, I've got another 7,500 examples. There's no discretization being done yet. This is the model. You could, for example, store this in your repository if you wanted to. This model will now be applied. If I run this model, run this process, here it is. Now what's happened is basically the attribute to discretize has been discretized, and sure enough it looks the same as it. It's different data, but it means that the important point to bear in mind is that you must do this if you are pre-processing data to build a training model. Then you must apply the same pre-processing to any unseen test data to ensure that your training model works correctly. So by doing this, by keeping a model, a pre-processing model, perhaps in your repository, it means you can very easily, in fact you must, it's very easy to just apply the model to your examples. It's very neat actually, but many people forget to do it, and as a result their training and test results don't seem to be very good. Okay. Last thing I'll do then is I think the one that people find the most complicated is this discretized by user specification, so I'll just bring that up. Leave that for a moment, and then I'll run this, do that. Scroll down and you can